Hello everyone, Mrs. Patel Dane here for topics 9.3, 9.4, 9.6. We're going to group a whole bunch of these together today. So all of these deal with Gibbs free energy. So essentially, we know we have enthalpy, delta H. We know we have entropy, delta S. Those things will kind of tell us whether or not a reaction is going to happen spontaneously. So for example, like delta H, if it's negative, it's exothermic, meaning it's going to release energy. Whereas an endothermic reaction, something that has a positive delta H, is going to take in energy. It's going to need energy in order for the reaction to happen. So something that would be more favorable thermodynamically would be something that's more exothermic. If we have something like, or something with entropy, for example, like we had in the last topic, something that's going to increase in disorder is going to be more thermodynamically favorable as opposed to something that's going to require it to be more orderly. So a positive delta S was more favorable than a negative delta S. When we combine those together, we get something dealing with delta G. G is Gibbs free energy. So it's whether or not the reaction truly is going to occur spontaneously or not. The others give you a clue, but this, when we put them all together, kind of gives you a better idea. So if we take a look over here for number one, spontaneous. So spontaneous reaction is something that's going to happen without an extra input of energy. See, so a reaction converts Rxn to reaction. A reaction occurs without, I use W/O for without, an extra input of energy. Meaning when you take those two reactants and put them together, it's going to go ahead and react. That gives us Gibbs free energy. If we use Gibbs free energy, we can calculate that in order to determine whether or not a reaction will occur. So again, Gibbs free energy determines whether or not a reaction will occur. So what we say is that this is thermodynamically, and I'm going to put this in a star, it's thermodynamically favorable. So we have to think about our values. We first look at delta G. We know delta, the change in G is Gibbs free energy. This little degree symbol, just to remind you, that means that it's standard condition. And standard means that it's going to be 1.0 molar if it's a solution, or 1.0 atm if it's a gas. If we had a positive delta G, this is thermodynamically unfavorable, so not thermodynamically favorable. And I'm going to just abbreviate thermodynamically as favorable. Whereas negative delta G is thermodynamically favorable. To remind you, I'm going to throw this over here. Let's see if I can get some space over here. So we can say that something that is thermodynamically favorable is a negative delta G, so a negative delta H, or a positive delta S. Something that's not thermodynamically favorable, on the other hand, would be positive delta G, positive delta H, or negative delta S. Cool. So if we're just dealing with delta G, and that's kind of what we're doing with this, at least for this page, we're going to talk about the value for pure elements. So just like within delta H, anytime we have pure elements, so any of the Hunkelgriffs, meaning diatomic, so H2, O2, N2, Cl2, Br2, I2, F2, or something that's just like carbon, all on its own. They're going to be a delta G value of 0. That helps us when it comes to number 3. So number 3 is having us calculate the delta G for the following reactions, giving the information for each individual component. You've seen this a bunch of times before, and this is actually going to be the same thing as delta H and what you've seen for delta S, products minus reactants. So that is going to be the sum of the moles of the products times the delta G values of formation, delta G values of formation of the products minus the sum of the moles of the reactants times its delta G of R. So essentially, again, it's products minus the reactants. So let's see, CH4, I'm going to fill in some of these numbers right over here. So I've got 50.8. Notice this is in kilojoules per mole, whereas delta S was in joules per mole. O2, it's pure element, that's 0. I still have to put in my equation, though, just to make sure that the reader knows that that is going to be the same thing. I'm going to fill in the values for carbon dioxide. And I did not give you enough space here. Sorry about that. And then water is this value. Again, I'm just getting it from the table that has been given to me, and I just know that oxygen is 0 because it's a pure element. So let's go ahead and take care of our products first. We have, and I'm going to put the products in brackets, 1 mole for CO2 times 394.4 kilojoules per mole, and then that is added to 2 moles of water times negative 22857 kilojoules per mole minus, I'm going to have to squeeze this over here. We'll do it over here, but notice that this, if I could have space, I would continue off to the right. So minus the reactants, which is 1 mole of CH4 times 50.8 kilojoules per mole plus 2 moles of oxygen times 0 kilojoules per mole. Again, you got to put it in because you need to show your reader that you know that that value is 0, as opposed to somebody else who, if they didn't write it in, we just assumed that they had no clue and just ignored it. So again, make sure you put in the right thing. When I throw this into my calculator, first of all, moles cancels in each one of these. All right, cool. So over here, I'm going to make sure I have my parentheses, and I'll keep pointing to my parentheses if I need to. I know I have 394.4 plus 2 times negative 228.557. Couldn't read my own handwriting. And then I close out that parentheses minus 1 times 50.8. And then I don't need to worry about this stuff over here because that's going to be 0. So here I got negative 113.54. The unit is in kilojoules, so this is my delta G. And it's standard conditions formation. Cool. So I've calculated that, reminding myself that, hey, this happens to be thermodynamically favorable because it's a negative delta G value. All right, coming down here, the delta G of the following reaction is, so this time will give me the whole reaction. So that is negative 2705 kilojoules. I'm just going to notice moles for this part. Sorry about having that in there. Determine the delta G of formation of C4H10. So this is my unknown. I know that oxygen will still be 0. My CO2 is given to me over here, and my water is given to me over here. So don't forget that's still over there. All right, so this time I'm just going to do it over here. So 4 moles of CO2. My CO2 is 394.4 kilojoules per mole plus 5 moles of water, and that is negative 0.57 kilojoules per mole. Close out that bracket, minus, open up another bracket, the reactants. This is X, plus 13 over 2. And yes, you can have a 13 over 2 number of moles. I know, it's weird. They just didn't make this a whole number coefficient. So they had to keep it as 13 over 2. Oxygen, and that is each going to be 0. Cool. So when I multiply or figure out this side over here, if in parentheses 4 times 394.4 plus 5 times negative 228.56. All right, cool. So if I need to kind of keep this simple, if I need to, it's 434.75 minus, well, this is equal to 0, so that's minus X. Bring this down if I need to, 2705. Oops, sorry, these should all be kilojoules, and I'm keeping kilojoules to make sure I've maintained my my units. And because that's minus X, I might move that X over, subtract out a negative 2,705 kilojoules, and so I'm adding it to both sides. So essentially, mathematically, I'm adding these two numbers. 2705 plus 434.75 gives me 3139.75 kilojoules. And then, I'm sorry. Yeah, this should be kilojoules per mole because it's going to be of this substance. So this is the delta G of formation for this substance right here. Right. Then next thing. So this again is using kind of what we've done before, products minus reactants, continuing that as we have done in the past. Then next page. This is when, hey, let's try to figure out what happens with enthalpy and entropy. So this equation is, I'm assuming in your reference table, I should probably double check that, delta G is equal to delta H minus T times delta S. So let me grab different colored writing utensil. Sorry for that. Okay, cool. So this unit is usually in kilojoules over mole. This unit is usually kilojoules over mole. Delta S is usually in joules over moles. So you'll have to convert delta S into kilojoules or to convert these two into joules, whichever one is best for you. Temperature can remain as, temperature should be in Kelvin, excuse me. So temperature is in Kelvin. My bad, I forgot. Delta S is joules over moles times Kelvin. So that's where my Kelvin cancels out from. So to remind you, I pretty much have 8 problems here, each of which do something different. So these first two, 1A and 1B, I have a negative delta H, positive delta S, but here I've changed my T's. One T is negative, the other one is very positive. Then, for my next two, I've kept a positive delta H and a negative delta S, so completely opposite of what I have here. And I've switched around my two temperatures, 3A and 3B. I've made a positive delta H, positive delta S, have those two numbers, and then negative delta H, negative delta S, and then those two numbers. So essentially, these problems are important because I'm trying to have you see what happens at like positive versus negative delta H, same thing with delta S, at different temperatures, at high temperatures versus low temperatures. So, we need to make sure we do over here, Kelvin. Temperature. Don't forget that Kelvin is equal to 273 plus whatever your degrees Celsius is. So because this is negative 200 degrees Celsius, I'm adding that to 273. So that should be equal to 73 Kelvin. Same thing for all of these. And then 2,000, not even putting that in my calculator, 2,000 plus 273 is 273 Kelvin. All right, cool. So again, make sure you have those properly written there. I'm giving you a bunch of space down here to work. If you need more space, go ahead and use more space. So 1A, I'm reminding myself I've got delta G, that's what I'm trying to solve for, delta H minus T delta S. So my delta H is negative 5613 kilojoules over mole minus my temperature, which is 73 Kelvin, times my delta S. Notice this is in kilojoules, so my delta S has to be in kilojoules as well. To convert joules to kilojoules, I need to divide by 1,000 joules. So I go 1, 2, 3, and like that. So this is 73 Kelvin times 0.0799, 11 joules over moles times Kelvin. Notice my Kelvins cancel. This actually, I'm sorry, should have been kilojoules, because I converted that over already. So now I've got kilojoules over mole minus kilojoules over mole. That mathematically will work. You can't subtract unlike units. So if I put this all in my calculator at one time, I can do negative 56.13 minus the product of, so putting that in parentheses, 73 times 0.07911. And that gives me negative 61.9 kilojoules per mole. So that's what I have over here, negative 61.9 kilojoules per mole. All right. I would recommend that you go ahead and do all of these on your own just to double check them to make sure that you are set. I'm going to do one more with you guys, and then I will fill in numbers for you. But again, make sure you know how to do the math on this. But math is not difficult whatsoever, but we want to make sure that we do not accidentally mess this up. So this one, my temperature of this one is 2273 Kelvin times 0.07911 kilojoules for every 1 mole Kelvin. My kelvins are canceling. So to put this in my calculator, I'm going to cheat a little bit. Let's see if you can see that. Cool. I'm just going to do this, and not necessarily cheating. I'm just using a shortcut. Making sure everything else matches up correctly. Cool. And then I get negative 235.9 kilojoules per mole. So we have 235.9 kilojoules per mole. So again, please make sure that you're going through these and double checking them, do your own, etc. For these, I am going to at least show you guys like what the values should be. So double check your own. Oh, I don't think I did proper sig figs on these. I'll get rid of that. And 45.16, 2.2. Oh, actually, that's 3. I'm using 4 sig figs. And again, all of these are kilojoules per mole. So what I'm trying to find here is what happens to delta H with delta H and delta S. So down here, I have delta H. Let's figure out first what happens when it's less than 0, meaning when delta H is a negative value. and then delta S is a positive value. So I'm taking from number 1, negative delta H. So I'm saying that delta H is less than 0. Putting that in there. Then coming back up, my delta S for number 1A and 1B were both positive. And so delta S is greater than 0. And then we're going to see what happens with delta G. We want delta G to be negative. So in both instances, it is negative. So at low temperatures and high temperatures. So delta G is favored at all temps. If this helps, let me color code these categories. All right, sorry about that. Okay, so let's say this section over here is highlighted in pink. That's what I'm dealing with these first two. My next two, I'm going to be in orange. So this one, delta H is positive, delta S is negative. Sorry for not being perfect on these. Okay, so delta H is positive, meaning delta H is greater than 0. My delta S on these were negative, meaning delta S was less than 0. And we're looking, is delta G favored? It is not favored. So, not favored at all. And that makes sense, right? Because if we want something that's exothermic, to be that if exothermic is favored and a positive delta S are favored, then neither one of those conditions had that. Okay. And then we're doing number 3. Right. So number 3, 3A and 3B, delta H was positive and delta S was positive. So positive delta H was greater than 0. We had positive delta S was greater than 0. And looking at this, we can take a look at low temperatures. Delta G was not favored, it was not thermodynamically favorable for delta G. Whereas at high temperatures, it was favored. So delta G is favored at high temps. And that value for high temps really depends on what your values for delta H and delta S are. All right, and then 4, it looks like both were negative. And just checking. Oh, this one I think should have been a negative number. So for 4A, make that negative 77.91. So for 4, we have delta H is negative, so I'm going to do a negative delta H down here. So delta H is less than 0. My delta S was also negative. And this looked like it was favored at low temperatures. So delta H is favored at low temps. All right, cool. So these are not necessarily things that you need to memorize, but as long as you can work through this equation, you should be able to kind of get a better idea of how to do those. All right, so that's if you need an equation with delta H and delta S. Number 8. Very familiar. It's kind of like Hess's law when we had enthalpy. Same type of concept. So for number 8, determine delta G of formation of graphite from diamonds. So here we've got carbon as diamonds, carbon as graphite. So to think about what the original equation is, let's make sense of this. We're forming graphite, so graphite should be in the product from diamonds. So diamonds should be in your reactant. So diamonds form, and both of which are carbon. It's just depending on how much pressure and stuff like that there is. So the carbon in the form of diamonds produces the carbon in form of graphite. So we're trying to see what that free energy looks like. So if diamonds is here on this row, use my highlighter. It's in my reactants. My graphite, however, should be in my product. So for this equation down here, I'm going to have to flip it. So I'm going to use CO2, gas. I'm going to line up my arrows and use C for graphite plus O2. And because I have switched my switched my equation, I'm making my delta G now going to be, before it was negative, now it's going to be positive. So that means that I have graphite in the products for both of those. So let's just double check. I can cancel out oxygen, and I can cancel out carbon dioxide. So I'm just left with carbon of diamonds produces carbon from graphite. And then I can take these two values and just add them together. And that ends up being delta G is equal to -3. And that's -3 kilojoules. So it's fairly spontaneous, but at least it does happen. All right. So for number 9, I want you to go ahead and do this problem. And then hopefully tomorrow I can go ahead, like when I ever see you again in class, whenever that might be, we can post it or I think what I want to do right now. I want you to do this. And then you can check your answers with me tomorrow, just to make sure that you are all set to go. And yeah, I'm going to end it right here. Have a wonderful day. Take care.